principals are rightly said, no, material process that depends upon the what you want, what property you want, what is the application you want to apply the materials, and based on that, you know, your based on the applications, your processing, your properties, your structure depends. So I will briefly touch upon a few important process and how to achieve the important properties or required properties. This talk basically I focused for the students. As Professor Arpita Chatterjee said, the second year, third year students will be there. So my talk is basically focused the basic learner of the material processing, and something for the faculty members also. So it's a mixed type of talk. I hope you will enjoy it. Before starting the talk, let me introduce our lab, CSIR-NML, Council of Scientific Industrial Research, National Metallurgical Laboratory. It started as 26 November 1950, so it's a 70 years old lab. Okay, so our lab basically 5 divisions, and we have around 10 groups, okay, and 4 supporting divisions: engineering, business planning, human resource, and all. And we have around 140 scientists, around 100 technical staff, around 100 administrative, and contract manpower around 350. Contract manpower means project assistant, research scholar, and some contract manpower. So total around 650 to 700. So some of the facilities, let me tell you what facilities we have. They're very brief. We have enormous facilities. Okay, some facilities created for the industry, benefit of the industry. For some facilities for the research purpose, for the students, for the faculty members, for researchers. So we have mineral processing from a small capacity to large capacity, 100 tons per day capacity. We have column flotation technology, which is very important and famous technology. We have been already commercialized, technology transferred and commercialized more than 10 places. So we have something 50 ferrous and non-ferrous extraction plants. And we do research on starting from materials, strategic materials to the conventional materials, tungsten to rare earth elements. We do a lot of projects on steel and non-ferrous alloys developments. So like our sodium, which is unique in India, probably no other lab is working on this, and no other industry in India is working on this sodium project. So we have a tungsten pilot plant, which is commercialized in many places. Now, we have very, strong surface engineering lab. It's very unique surface engineering facilities, and probably one in the lab, the hot dip process simulator is unique in our lab. So we have very strong analytical chemistry divisions. We produce, sell, CRM, certified reference material. Most of the industry, they take this material for their reference. And we have very, very super projects, high value projects like advanced ultra super critical boiler power plant. We do amorphous electrical steel research. We are planning it because this CRGO steel, this amorphous electrical steel, CRGO steels, it is not produced in India. So we are in the process of doing a lab scale. We have several very strong and NDT facilities. NDT research on it is highly acclaimed among the industries, like Mixter, FlowGuard, and all these things. The technology already transferred, and we have largest PEEP laboratory in our lab. It's the second largest in Asia, probably second largest in world also. First in NIMS, Japan. Then we are the second place. We have the best fatigue and fracture lab. And the group in which I belongs, basically our group is do a lot of alloy developments, including ferrous and non-ferrous. We have very unique facility on hot dip coating, that I said. We have a lot of, facilities. Enormous list is there. We have a full characterization facility like XRD, transmission electron microscope, ACM, IPMA, energy probe, electron probe microanalyzer, atomic probe microscope, and so on. Enormous facilities we have. Okay, and for mechanical students, intentionally put this, we have sheet metal forming testing machines. You probably know this machine, and we have the Glibel, that thermomechanical simulator. This is unique in our lab. A very few labs and few industries have it. So this is, I mean, at the end of my talk, I'll discuss more about this. So you are, of course, after this pandemic, if anybody wants to visit our lab, you are welcome. We'll take care of, I mean, you can write to us or write to me. We'll take care of your visit to our lab. Okay, so that's in a brief, the lab which I belongs. Now, coming to the main topic of our talk, materials process. I mean, before that, first you have to develop the materials. So for developing materials, first you have to select the materials based on your property requirements. As principal sir said, so what's your requirement actually? What property you want? What strength? What yield strength? And what yield strength to, UTS ratio you want? Or in simple words, what ductility you want? Okay, that depends on the what materials and what process you apply. So first thing, any material development, first you have to do casting, then all processing, I mean secondary processing, say solidification, say further rolling, forging, and so on, and finally application testing, and finally applications. So before that, if we go for, very simple example I'll take, if you go for world car population, it's increasing enormously from say 2010 or say 2000 to 2020. It's a threefold increase in the developing nations. But threat is accelerated greenhouse emissions, increasing fuel price, and limited fuel resource. So there is a need to develop the lightweight automobiles or lightweight materials, which will give the concept of like 3 liter in 100 kilometer or 2 liter 100 kilometer cars. Because World Bank has estimated in 2030 the vehicles, emissions from vehicles will multiply several times. And for that, if you can reduce the 10% vehicle weight, there's a 7% fuel saving. You'll be surprised to know that 100 kg mass reduction in a vehicle will reduce 8 gram of CO2 per kilometer at the exhaust pipe. Hence, the developing nations have the greater challenge to reduce the pollution from the transport sectors. Now, our challenge is to develop how to develop the lightweight materials, starting from the steel to non-ferrous alloys like aluminum alloys and magnesium alloys. So that, if you see, this figure is quite old figure. If you see at present, not at present, if you see from this figure, aluminum is 30%, steel around 40%, plus 10% hot form steel, aluminum casting at 12%. This is a quite old data, but if you see, I'll show you that in today's scenario, everything has changed towards the lighter materials. But at the same time, lighter materials, but you have to improve your safety of the passengers. So people started the concept of hybrid body structure, like what most of the automobiles are using that. Now, lighter weight materials, aluminum, people compare North America to India, our use is very less, say 260 kg at present. So if you catch up the trend like Europe, Japan or with North America, then our, growth of research on aluminum component development is almost threefold, 3 times. Okay, just imagine. In fact, China, North America compare China, China is slowly developing, slowly going up to use the lighter weight materials. Like intentionally I put this slides, the aluminum body seat growth. I mean, people are trying to complete automobile seats. Being a mechanical, students, I just concentrate my talk on mostly on automobiles sector, very less on materials, on metallurgy aspect of it. So the aluminum seat growth is slowly increasing. Say, from 2014 to 2030 projected value, the pounds per vehicle is steeply increasing. Same from this graph. Now, most important, the automobile manufacturer, among passengers, the outlook are slowly changing in order to reduce the vehicle emissions. People are now, across the globe, people are now trying to develop the full-fledged electrical vehicle. Initially, the IC vehicles, they dominated the market, then hybrid structure. Now concept changes totally to the electric vehicles. Now for this, you have to really develop, you have to change your processing parameters, your materials development, your property requirements towards the more and more lighter materials, starting from aluminum, magnesium, and steel. So some of the few examples of aluminum and steel, I'll just highlight in my talk. Okay. So just imagine what I said a few minutes back. In 2009, the steel used almost 80%. Now, steel consumption is really very less, so around say 10%. Is a projected value of 2020. Actual value, yet to, I do not know the actual value. Okay, so around that. So the use of aluminum and magnesium and composite are enormously increasing. So if you see in the casting business, so mostly the die casting and permanent mold casting from this figure. So in my talk, we'll see how we'll improve the properties in die casting and also permanent casting. So before that, if I see the casting, what is casting? Very simple, fundamental, because I understand some of the second year students are there. So for them, maybe some of the students are new to this topic. So casting is the, metals of these are safe, which is produced by pouring molten metal and allow them to solidify. So casting may be ferrous and non-ferrous. Now, why casting is so important? Because of the high demand of the casting, especially for the lighter weight casting materials, lighter weight materials. So casting is very important. So to understand casting, it's not like just you melt and pour. So in my next slide, you'll see the various steps of casting. First, you have to take mold, then you have to melt. So melting, the moment you do melting, the liquid metal has a high tendency to absorb gas. So imagine for aluminum alloy, at this over the melting temperature, it's already 1 cc at 100 gram, 1 kg, that is 10 cc of absorption of hydrogen. It's huge. The moment they will solidify, the solubility of hydrogen in aluminum is very less. So all these gases has to go out. And most of the people, most of the researchers, most of the students, they don't take care to reduce all these gases. As a result, the moment you do casting, all the gases are inbuilt, included in the final casting, and they have very less properties. Similarly for steel, similarly for copper, magnesium alloys. In all cases, the moment you do casting, please take care to eliminate completely the dissolved gases. Otherwise, you won't get sound casting. And that's the reason most of the people, they import the sound casting. Few examples I'll give you. If you give the improper degassing, this is the result. Lot of blowholes will come in the cast product. So all these blowholes will eliminate if you take care the degassing part of it. And if you see degassing, there's several degasser techniques are there, rotary degasser, and many techniques are there. But whatever technique you will apply, please see that whatever way you will degas, mainly by argon or by nitrogen, is just to cover entire area. And the way, the pressure of this argon or degasser depends how much material you will take in your crucibles. So all these calculations you must do and then degas, so that all elements, I mean, see, this I put, the argon or nitrogen, depending on what material you are taking, and it's just to percolate entire melt, so that all the dissolved gases should come in and go out. Similarly, not only degassing, the pouring, most of the researchers I find, they simply melt and pour, but they never take care the turbulence in pouring. The moment more turbulence, lot of gases will come inside the material cast, mold, and finally to the cast product. So your pouring, the height should be minimum. Now, if we talk the different casting process, mainly I said most of the industry, applications, many cast products are there. Either permanent mold casting or the pressure die casting. That's the two things I have highlighted only in the casting process. So gravity casting, either sand casting or maybe permanent mold casting. So in sand casting is a very common practice, maybe 100-150 years old process, but still a lot of things can be improved upon this. So people or industry do green sand mold, either silica sand, or maybe for special sand, for special steel casting, chromite sand or zircon sand, what to make green sand mold by bentonite and some additive. Okay, and require amount of water. When you do casting, please take care, right amount of water, right amount of all these things. So the mold should be sufficiently hard. The mold erosion should not be there. Like sand casting is a really very flexible. But virtually all types of casting you can do by your sand casting. Same properties in all directions, suitable for simple and intricate shape. But lot of limitations for this. Lot of, as I said, porosity, gas holes, and interdendritic shrinkage, like all these dendrites, which leads to very poor mechanical properties. So what's the way out? Now your things is you have to put the riser. But this, when you put this riser, people they put riser, but they never consider the design of the riser. They put riser, but this runner, you take care of the runner and all in the design, so that the riser material should be solidified at last. Because when this your metal casting should solidify, whatever shrinkage takes place, the riser should feed enough material to compensate that shrinkage. But in most cases, it is observed that this riser, this runner area is so small that it solidifies fast. So no use to put this riser. So please take care when you design something, design a new cast product, when you want to really minimize the gas holes in your cast product. But still, limitation is sand cast is the very low mechanical properties. For example, say aluminum silicon alloy, 120 MPa. This value you note because you will see at the end of my talk or the middle of my talk how this 120 MPa can be enhanced to a several fold. This example, always aluminum silicon, I'll take, I'll show you through changing the process parameters how we achieve the both strength and ductility. One simple example I have given you, I have highlighted in my talk. So to overcome this, now you need the faster solidification, that is the permanent mold casting, which most of the industry, they do the permanent mold casting. So it's a permanent mold casting means your solidification rate is faster, so fine grain size, good surface finish, and superior mechanical properties compared to sand mold. But still, lot of porosity is there in say aluminum casting. You can find like very fine pores, but not suitable for mass production. But in permanent mold casting, we cannot cast the intricate shape, no big casting. So what is the way out? So then we do the pressure casting under very high pressure, where we don't need any risers, and very accurate dimension accuracy, excellent surface finish, very fast. So this pressure casting, either high pressure die casting or low pressure die casting. High pressure means and high velocity. Velocity is up to 80 meters per second. You can imagine. So filling time is just a few milliseconds. And course you will not present. So HPDC may be cold chamber die casting, hot chamber die casting, depends upon the what industry, what product you are making. So you can choose on that and what alloy system you are taking, what property you are taking. So you can choose any of this based on your requirements. So in hot chamber, this is a textbook phenomena. I have given some, maybe I have taken from some text. Okay. So similarly, the cold chamber again is taken from your from textbook or from net. I forgot to mention the source here. However, in cold chamber, from the melt you take the ladle and put in the short sleeve, and then close plunger it already closed, and they push inside the die, and you get the final product. However, so advantage of HPDC is a near net shape production, high productivity, when thin wall can be made from this HPDC. Okay, but still limitation is the gas porosity along the parting lines. So gas porosity is a problem in all cast product. So now how to minimize? Okay, so another technique is the semi-solid processing. So before coming to that, so if you see the cast structure, when you put in the mold, permanent mold, first equax grains, a lot of columnar growth takes place, and central equax zone. So your aim will be how to get totally equax zone, so that you will get uniform properties throughout the cast product. So for that, we do the inoculation and the grain refinement, phase modifications, that I'll discuss in my subsequent slides. Now, so if you talk again the steps of melting or steps of casting after pouring, degassing and final pouring. Now the control of solidification, how to control the microstructure. That's the backbone of any materials development. Unless your initial structure is sound, whatever process you will adopt is no use of it, because the base structure is something faulty. So you have to really take care your solidified microstructure. Here the three process variables you have to take care: velocity, temperature gradient, and alloy composition. Of course, several physical phenomena you have to involve in it: solid diffusion, thermal diffusion, and all these things listed here. And microstructure transition may be planar, maybe cellular, maybe dendritic, and maybe eutectic. So dendritic structure, now how to reduce the dendrite, how to reduce the cell tip radius, dendrite tip, how to decrease the primary spacing, including the interdendritic spacing, the secondary spacing, the eutectic spacing, that I'll highlight in next in my talk. Because in all cast structure, the dendrite tip is very detrimental. So tip of the dendrite acts as a stress razor, so thereby very low mechanical properties. So the moment you do solidifications, I mean, few little 2 slides are very basic in fundamental nature. After that, I'll give some practical examples. No more fundamental talk. I think I thought that students without this little knowledge of how the solidification takes place, they will not understand the further process. That's why I included these 2 slides. Okay. So the solidifications, the driving force is the change in Gibbs free energy. So Gibbs free energy, this calculation is just in a standard textbook. I mean, definitely the second year students, probably you know this. The Gibbs free energy is proportional to the undercooling, because to solidify we need to undercool the material, and that undercooling is a driving force of solidifications. Okay. Okay. So this solidifications takes place by homogeneous nucleation or by heterogeneous nucleation. So homogeneous means you don't add anything. I mean, that nucleation takes place in the melt itself. So it is very difficult to achieve, and for that very high undercooling is required. Like this, very high undercooling. Say aluminium, just imagine the melting point of aluminium 660, and you need say 656, 4-degree undercooling to start off solidification. And then again, the moment your solidification starts, recoalescence and latent heat, again temperature will rise. So growth temperature here. So this now your aim will be how to reduce this undercooling so that the entire mold, entire melt will solidify at one moment. So we'll see that. Okay. So you can do by heterogeneous nucleation. So the Gibbs free energy change by this equal to homogeneous into some factor. This you can calculation is there. So you have to choose theta, that is the inoculant you will add in your melt in such that it must have low weighting angle, say around 10 degree. If we put a 10 degree here, we'll find that really this is very, very less. Moreover, again, you will choose the inoculant such that the interfacial energy of the particle melt should be very less, than the solid nucleus and the melt. Okay. So this inoculant will add, as I said, the dendrite or the interdendritic space you have to reduce by grain refinement mechanism. So why will you add grain refinement? For improvement of structure properties, better deformation characteristics, improving casting speed, and reduce the hot cracking. Like as I told you just now, you need really very high undercooling, here 4 degree. Why? Why not? At 660 it will solidify, because the moment one nucleus start in the melt, one surface created, so it has surface energy, there's volume energy. Volume energy is negative, surface energy is positive. So 4 pi r square and 4 by 3 pi r cube. Please note, it's not 3 by 4, 4 by 3 pi r cube plus that energy. Initially it is positive. So you have to overcome that. You have to cross the critical radius. The moment you cross the critical radius, then only the nucleation starts. So for that, you need some high undercooling. Now, how to reduce this undercooling? How to avoid this elongated grain structure in homogeneous nucleation? See, here 660, but nucleation is above the good temperature. Earlier I showed you 4 degree, here 2 degree. Now you will see some cases that nucleation will start really at high temperature. So if you can do that, the entire melt together at the time, you can start your nucleation and growth, so that there is no time for the elongated grains to develop. I'll take the example of say aluminum alloy. We add the aluminum titanium alloy, and some cases aluminum titanium boron, to do this. here I showed, see, 660 aluminum temperature, but nucleation temperature is above that. So before solidification of the aluminum, your nucleation starts over here, and that you need to get very fine grained structure. Okay, so that, and it is sufficient amount of L3Ti, sufficient amount of aluminum titanium boron, you have to add. Boron intentionally we add, so that a lot of Lb2 Ti-B2 particles we add, so that you can add as a effective nuclei to protect the layer of L3Ti. I mean, a lot of research has done on it. In India, many people have done. Professor Pai, Professor Chakraborty, Manishan Chakraborty, and all his students. They did. Professor Murthy, they did a lot of work on this aluminum titanium boron. For example, I have taken one example. How to modify the structure. Very interesting example. It's my own work, my doctorate PhD work. It's a long back. So here, if you take aluminum, 8% iron, vanadium silicon alloy, this alloy is used for, say, your rapid solidification technology. So can you imagine, structure is very coarse, highly elongated structure, all these dendrites, all this elongated structure, so no use, very less properties. The moment you put in mold casting, permanent mold, this is sand mold, 1 degree Kelvin per second, this is sand mold, permanent mold, 14 degree Kelvin per second, your structure totally changes, very interesting structure, star shaped structure, but no use of, for this, because strength only 100 to 110 with elongation same, so no use of it. The moment we modify, imagine I have introduced this nickel magnesium in aluminum alloy, this is the first time, and I have taken patent on it. So that structure totally modifies, totally the spheroidal shape change from this dendritic structure, this star shaped structure, to this. So strength 320 with elongation almost 9%. By further post TMT, thermomechanical gap processing, structure further improved to 380 MPa. And some of the precipitates I have extracted from the matrix. Okay. Now, so next is now how to improve these properties. One is the grain refinement, and that is semi-solid processing. Why? Because always your aim will be to break the dendritic structure by formation of globular. So if you can break the dendrites and form the globular structure, so that your strength, your UTS and ductility both will improve a lot, and also you can minimize the hot tearing tendency. Okay, so semi-solid processing, semi-solid casting may be thick soap forging or rio casting. So in thick soap forming, you have to really prepare the feedstock material, then heat inductively or in furnace, and make a semi-solid and put in the in a sleeve or high pressure die casting, so that you can make the required shape of the casting and required shape of the desired product. And rio casting, this facility we have in our lab. So rio casting involves, so you start the melt in between the solidus and liquidus, because massy zone is there. So that all the dendrites form is now broken into smaller pieces for the solidification, and will take some of the globular shape of the casting. For example, I have taken, so if you do the conventional casting, the same alloy, aluminum silicon alloy, 120, but rio casting will give you little around 200 with ductility, say slight improvement in ductility. But you can notice that primary aluminum is globular, but all this dendritic structure still the elongated, say around several micron, more than 50 micron. Please note this, more than 50 micron. So we'll see in our process how this 50 micron can be converted into few nanometers. Okay, and all these alpha grains can be again reduced to a few smaller size to improve its strength to multiple fold. Okay, So this radiocasting parameter, there are several parameters you can control based upon your property requirements. But one problem is there. The moment you do, okay, the radiocast structure. So imagine this is a 357 alloy. This is the ASCA structure, all lot of dendrites, and final semi-solid structure, all the dendrites, I mean primary alpha, totally round, totally spherical, and here interdendritics, casting shapes are there, interdendritic phases are there here, which are basically a little bit elongated, magnified structure I'll show you. But the problem here is the moment you start in a solidus liquidus temperature, as the solid content increases, pouring is very difficult. So that is the way people have developed the Rio die casting. That means you do the Rio casting over here. Professor Fan, Brunel University, basically he has developed this in this technology. Some of the industry are now adopting this. So here you do the Rio casting, and then with the twin screw mechanism, all the slurry content you just remove and put in the SPDC. So this is highly improved property with high productivity. This is a newer casting technology. Probably hope it will come in a big way in coming days. So if you compare the cost performance with forging process, squeeze casting, all this process, the Rio casting here, forming cost is low and component property is very high. But still, lot of parameters need to improve in the Rio cast processing parameters. Another way of to improve the globular structure is the SEMA, a very little newer concept, strain-induced melt activation. Now I find lot of mechanical students, in fact they work on material, either composite or semi-solid processing or on SEMA. In fact, my 2 or 3 of my PhD students, they work on semi-solid processing on composites. They are basically from mechanical engineer. Okay, so that's why I intentionally put few slides here. So this is newer technique, relatively say first last 10 years and so. So this, why this? So this is required to enhance properties, to produce the desired structure what you want, and to reduce porosity and segregation. So this SEMA process, the strain-induced multiplication process, consists of 4 discrete steps. First thing, you cast, you cast in a desired shape. Then you break the, hot work to break the dendritic microstructure or reduce the thickness. Then you warm work, not hot work, because what you have to do the below recrystallization temperature, either cold working or do warm working to store some energy and do partial melting, say 10 to 50% liquid, and hold isothermally at desired temperature and time, so they will convert into totally globular morphology. For example, same alloy I just taken, Rio casting, conventional casting, Rio casting, and then this is the the SEMA treatment, so that you can increase your strength and ductility both. For the SEMA plus aging, further you can improve your properties. So, but this SEMA, maybe, this SEMA technique, I says rolled and then heat treatment is applied to the very thin section of the casting. So maybe by the aluminum alloy body structure, it's a good scope is there. Good scope is there to do research on this, and people are trying to develop this. Next is composite. Not only alloy, lot of people are doing the business on composite. So metal matrix composite, and some of the people the composite. What is composite? It consists of 2 or more constituent elements, materials. They remain separate and distinct. And composite, they should not react with each other. They must be chemically inert. No, that's a basic definition of the composite. But in some cases, they may diffuse. No, to make the good interface bonding between them, so that the bonds strength will be very high. Maybe metal composite nowadays very famous. So fiber plus matrix composite. The matrix may be all these non-ferrous alloys, aluminum, magnesium, copper, titanium, and your enforcement may be silicon carbide, carbon, alumina, or combination. Fly as a lot of other people they are doing research. I hope some of the people, students or faculty, probably they are doing on research in composites. So we produce, a good way either stair casting or Rio casting, because composite making has a lot of difficulties because of non-uniformity in the microstructure. So we have this Rio casting setup with our you can make efficiently with this setup. So problem in the composite making, as I told you, the flotation and sinking. If you use the fine particles, it will float. If you use the heavy particle, it will sink. So debonding is a major issue. Segregation, non-uniform structure. But all this problem can be solved if you really properly design the Rio cast parameters, Starrer addition technique, and really the particle and the matrix. If you take care, you have to see what elements will weight. Your weighting will be more for the added particles. You have to see that. So this is the some of the setup we in our Dr. Poddar, he made all this. One of my student, he's a scientist over enable also. He made all this casting. Say Rio cast product. So this 20% SiCP, magnesium 20% silicon carbide particle. So you can see uniformly we are able to make these composites. So composite, the newer light weight is really very demanding materials. Proper bonding and uniform distribution is a challenging issue. And there are a lot of improvements of any alloy is very demanding. Okay. So one example I'll give you. As I told you, the aluminum silicon alloy, which is a very old alloy, and most of the industry they are using this alloy. But strength is, I showed you 120, which is 12% or 10% elongation. No. Now this aluminum silicon alloy, industry, they use grain refiner or eutectic modifier, and some people they use the semi-solid processing, but no significant improvement occurs. Okay, a few literature reported the SEMA significant here the significant improvement of mechanical properties through this process, and I'll show you. Here I've showed you the phase diagram, because most of the students, when they do some project work, they do some research, they never follow the phase diagram. This is the first thing a researcher, a student must use, the phase diagram. That's why I put this. So three compositions we have taken: 7%, 12%, 14%. Mainly I concentrated on 7% aluminum, 7% silicon alloy. The Ascar structure, you can see all interdendritic structure, lot of elongated shapes. So due to these shapes, the strength is very low, 117. Please note this value, 117, 16%. We'll see how this 117 goes to nearly 400. So with average grain size, say around 260 micron, plus minus this value, with highly elongated structure. Further, if you vary the silicon percentage, not going on these aspects. So very small concept, difficult to understand for the students, but still I'll try. So how to make the lightweight? So one of the way is the lattice expansion. If you can add lighter elements in steel, say for example aluminium in steel, you can substantially reduce the weight, and you can if you expand the various lattice, so weight will be reduced. At the same time, you can increase the strength part of it, so you can reduce the section thickness. So ultimately, this is the last slide probably. So ultimately, this 4 technique to increase the strength of any materials, so you have to pass through all these 4 areas. One is by grain refinement, which contributed around 50 to 60%, as I said, grain refinement. Then solid solution. So solid solution strengthening, which contributes around 20 to 30%, say. Various formula is there. And then one by taking care of the dislocations, contribution is very less. And last is the precipitation. Okay, so if we can control, if you can engineer all these 4 parameters, you can achieve to a desired strength and ductility both. Okay, so in nutshell, I can say, so the processing is based on materials and property requirements. What materials you want, what property you want, so that your process parameter will depend on that. But for mass production, die casting is very commonly used. Semi-solid process is a major future prospect for mainly for non-press alloys. Alloy development is one of the important area for intensive research for widespread application and physical, simulation. For example, say Glibel, hot dip simulator comes to rescue when alloy design and understanding of the process are required, because if you do a lot of trial and error method, it's a very cumbersome technique. But all these Glibel techniques, unfortunately, with these 2 techniques we have in our lab. And 3D printing is a really futuristic process for complex design. So these are the, acknowledgement, the contributed to my talk. Professor Chaudhary, who is my student, first 3, Professor Dr. Poddar, who is our scientist also at our lab, Professor Vinkot, again he is a professor in some college. Now all are rest of my colleagues over here in NML. Dr. Sandeep Ghosh Chaudhary is the head of Materials Engineering Division, and the special thanks to our director, Dr. Indranil Chattoraj, for his support and for permission to present this talk in front of you. So NML is committed for the industrial and societal needs. Thank you very much. So really, if you want to do something, venture outside your comfort zone. So I believe recognition bound to come. Thank you very much.
Thank you, sir. Before concluding your session, if anyone asks any question to sir, they can ask to sir. And sir, I personally have few questions regarding manufacturing. So may I, sir?
Yes, please. Yes.
So my first question is, if a new composite manufacturing, if anyone is interested for a new composite manufacturing research, then for the material, what are the basic tests he or she should perform, and how to calculate the ratio of the material and the reinforcement?
Yeah. First thing, for application, I said for application, what property you want. Okay. So whether you are looking for non-ferrous or ferrous material. For composite, if you want to work on non-ferrous, say aluminum base or magnesium base, based on the what weight and what property you need. Okay. Before that, say aluminum alloy. Now you want to develop something new. So a lot of people are not doing the the fly ash. A lot of people are now working the waste product from the colliery overburden. Lot of people are now using the boiler power plant waste to making the composites. So first thing you have to calculate, you have to know how much the weighting of your reinforcement to the matrix and how to improve it. Lot of data are available in chemical handbook. So from there you can calculate something, the weightability, weighting angle, all these things you can calculate. And now, after that, now you have to really know the base alloy, how much is the massive zone, that is the solidus and liquidus region. And for that, what method you will apply. If this is less, you can go for star casting. If this, what the conventional casting of composite making above the liquidus temperature, if that is high, you can go for Rio casting, so that all these components you can really capture inside the melt. Okay, and for property requirements, really from lot of formulas are available. The contribution from matrix, the contribution from the particles, the calculations there. It was there in my slide, but due to more number of slides are deleted. So you can calculate any standard is just textbook on composites. Maybe that Chawla, KK Chawla, and all the KK Chawla and some Chawla and Chawla. That book that discuss a lot about this composite. You can refer that. Yes, next question.
Thank you, sir. So the next question is, if any leakage will formed in casting, then what kind of chemical will be used for repair of casting?
Leakage means I don't know what you want to say. Leakage. Leakage.
Yes, sir. This question is come from Tathagato.
I don't know.
So Tathagato, can you please?
Yeah, what do you know leakage? Casting defects.
Yes, Tathagato, can you explain, sir, what sir asking?
Yes, Tathagato, can you tell me what is leakage? What do you mean by leakage?
Sir, he said
yes, Subhadip.
Yes,
any material factor.
Still I do not know material factor. I do not know. However, Tathagata, you can mail me a specific where is what do you know leakage or factor. Then I can able to understand. Answer you.
Tathagata, are you asking about casting defect?
Yes, ma'am. Means after casting any that product will be getting any fracture, then any chemical we use for
salvaging,
the repairing that
repairing. Okay. So repairing,
Yes,
most few industry, most people they do some sorts of repairing, but for repairing again you have to really see the same material has to be there, nearly same material, how they are bonding and what technique you are using. Say you are doing by welding, some putting the joining or extra material you have to put. Okay, but this salvaging technique for high-end application is not at all advisable. But for low-end applications, yes, some techniques the industry they do some salvaging technique. They do by filler material, they add some defects by filler material, whose property must be same with the parent material. Otherwise, there's no use.
Okay, sir.
Yes.
Okay, sir.
Thank you, sir.
Thank you, sir. The next question is, sir, in automobile sector, I have seen in a few articles or in any show that they are using carbon composite sheet or carbon sheet for manufacturing the body of the automobiles. Sir, so what is carbon sheet or carbon composite sheet?
Yeah, see, carbon composite is basically layered graphite composites. Okay, lot of research is going on that. So both carbon composites and both hybrid structure of carbon composite with the metal composites, are in use. A layer by layer structure people are making, and that some composites, one carbon composite again some layer again some metal composites. Okay, so they do lot of things. So they both strength and ductility, that absorbing strength, the graphite is in between, so is there. So you can improve both in energy absorption. You can improve both, strength and ductility by that way.
So in carbon composite sheet, what is the reinforcement?
See, in carbon composites, that reinforcement material itself is a carbon.
Okay, sir.
Okay.
Understood. So the next question is electric cars. Now electric cars is in trend, sir. But in India, what we see, the maximum percentage of electricity is comes from the thermal power plant or thermal sector. So is electric cars are that much beneficial to the environment if we do not
No,
change
no,
the
no.
power electricity sector?
No. Electric car means it's a battery operated, whether you can charge to a, like whatever car we are using now, fueling, go to the petrol pump and put the fuel, put the petrol in your tank. The moment electric car means it will run on the battery only. Most of the now people are putting the solar panel on the car so the battery can be recharged. And some of the people, they are really designing the battery so that it can run more than several days. And then go to the not petrol pump, go to the charging station, put the plug of the battery and charge, say, within few minutes. Now the challenging is instead of petrol, putting the petrol, or instead of petrol pump, going to petrol pump, you go to the charging station and charge your battery. And that battery charging should be like filling time of the petrol, say few minutes. So now a lot of people are now doing that research only. How to increase, how to decrease the charging time, how to increase the efficiency of a battery. Okay, a lot of battery research is going on. Many research is going on battery applications. Okay, so nothing related to the power plant or nothing related to the conventional generation of electricity. Okay.
Okay, sir. So the next question is, so what is the difference in aluminium 6061 and AA6061? What is AA6061?
That is such, I do not know. I can tell right now. Specific on aluminum 6061 and AE.
AA double A.
That you saw some specific composition or specific property. 6061 basically aluminum, silicon, copper. No, a lot of 6061 is basically used for aerospace applications. Okay, aluminum, silicon, Mg, and some copper. 6061, 6061, 6063. Basically these three, and AA, AE, all these things. You specific properties, specific tempering up, all these applications are there. Several varieties are there. I don't remember right now. Okay.
Okay, sir. So few minutes more. Another question is,
yes, please.
Sir, we know for manufacturing turbine blades or aircraft blades, creep testing is most important. We have to do creep testing. Is there any replacement of or if we do not want to do creep testing, any replacement that can replace creep testing?
No, creep testing has to be there. Now you can do the accelerated creep testing by indentation mechanism. We have some machines, people do that, but creep testing, you has to be there. That's why in some of the our creep lab, they continuously running for 24/7 for several years. Okay, but you can accelerate the creep testing by increasing the load. Where at what circle will do the creep testing. Suppose, for example, I'll tell you. Suppose with temperature, you want the load, maximum load by some application can go to 500, okay, or 600 MPa. So you do at 600 or it will 700 MPa load. You do at temperature, say requires 200, you do at 250. So like this, at accelerated test parameter we can set and we can predict, what should the actual that data will be. But most of the key parameter, they want the actual process parameters, which runs even years together continuously. And of course, nowadays, few people, few industry or paper, they reported the indentation creep testing for the accelerated testing.
Okay, sir. So the next question is why we used carbon fiber in sports, automotive, and in bike also.
Uh, that's maybe some specific property, specific requirements, which I have not much idea about it.
Okay, sir. So one last question is, sir, in this pandemic crisis, we all have to do practicals on online basis. We can't afford to go to college and do it by our hand. So, how much you think it will impact the future mechanical engineers in their
Yes.
job sector or anything else, future their job sectors or
See,
workings?
yeah, this is very, very vital question, very good questions, really. Now, our system has to the acclimatize in the present environment. Like few months back, nobody was thinking how to enhance the immunity. You know, like same thing, nobody was thinking to get the degree online. Few years, this conception started few years back, but people thought, oh, online degree is not possible, it's useless. But nowadays, I mean, you have to adapt yourself. If it continues, one is to adapt yourself to get the maximum benefit of the online. Okay, the theoretical things, the professors, they can talk. I mean, the practical things, which you go to various industry to see the things, which you go to college, if you have good facilities, to see in your own eye, to do by your own hand. But if you cannot do that, at least if your college, is very difficult, no doubt of it, but at least you can know, you can visualize how it works by knowing some online things. A lot of YouTube channels are there. A lot of colleges now, they are showing online the demonstrative purpose of the certain labs. They are online, they are showing as if you are doing your own hand. The professors or the attendants, they are doing by your own hand, and you are doing. And some people, those who are taking some training, and somewhere I've seen they are doing the online live telecast. So this is the sample loading. This is the as if you are seeing in presence of it. Okay, so sometimes we do in our training to the faculty members, or to the when do some course, say metallurgy for engineers, or the faculty development program. We do a lot of faculty development program. I think this Monday or last week of this month, we have some faculty development program. There, some of the facility are shown online. Okay, so no doubt the benefit you cannot achieve that that way what you achieve do offline, but still you have to acclimatize yourself, you have to accustom yourself to get the maximum benefit from the online. There's no alternate way. Yes, please.
Okay, sir. Thank you, sir. No further questions from my side, and nothing from our audience too. So thank you so much, sir, for your great words and sharing your knowledge with us. I hope it will help us a lot to be better professionals, better industrial professionals in future. I guess everyone have their doubts clear. Thank you so much, sir. Now, before ending the session, I request our TIC, Subhashish Haldar sir, to give a vote of thanks to sir.
Okay, thank you, Subodhi. Thank you, sir. So it was a very wonderful session, and it was a nice walk through the lab. And this session was very informative, and hope all the faculties and students, we have learned a lot from it. And this one good proposal you have given, so that we can, since we are hoping that the pandemic stops and we have the fortunate to visit the lab with the faculties and students, and it will be better if we it will be more better if we can perform any experiments there, or say research experiment or research related experiment there. So if that kind of permission is given, so it will be wonderful. And this session, I think we have learned a lot that how degassing, okay, is necessary. Okay, how degassing of say like casting is necessary to improve the mechanical or get the superior mechanical properties. Okay, so I think we have like this session was very helpful for us, and hope we have all learned. And the mistakes, okay, like suppose the casting that we do in our even though we are not having proper instruments, like how degassing can be done. So hope we can like inculcate this sort of knowledge more into our lab. So thank you, sir. Thank you once again. So hope we can have further session with you in future. Thank you, sir.
So thank you very much. So any faculty, any students, if still they have some specific questions, some facility and all these things, they can write to, I mean, to me or through Professor Chatterjee, to Professor Alpita Chatterjee. Then not an issue. Okay.
Okay, I
Sir,
will share, sir. I will share your email ID. Okay. Okay.
Yeah. Thank you very much.
Thank you, sir.
Hello,
Yes.
Hello.
am I audible?
Yes,
please.
yes.
Yeah. So one question before conclusion. So what we have to do if we want job in casting sector, in casting industry?
That's a million-dollar questions. Yeah. If you are interested in casting, I mean, industry at the BTech level, I mean, I really no idea how, I mean, you have to apply or through your college TNP, college training and placement division. You have to approach to them and they to approach to various industry. If campus interview is not there, or force application to various industry. But prior to that, you have to really gain acquire knowledge, certain projects in casting, and tell them, I have done this. You know, like one of my students, I tell you, he's done a lot of Professor Chandra Chaudhary. Initially, after just PhD, he immediately joined to a good casting industry, very renowned casting industry, and immediately applied some of the techniques. Now he moved to a college, a certain college, for better position. So gain some knowledge of casting, do something very special, and approach the industry. But above all, being a BTech students, I know it is very difficult. Practically is difficult. So you have to really approach to your TNP cell.
Okay, sir. Thank you, sir. Thank you so much. With that, I am concluding this session. Thank you to everyone. Thank you to sir, especially. And a special thanks to Arpita Chatterjee ma'am for organizing this webinar, this so informative and beautiful webinar. Thank you to our HOD sir for welcoming our guest and with his wonderful words and give a vote of thanks. Thank you to all the people joining us here in the GMeet and watching us on Facebook Live. Thank you to all. Thank you for joining us today. With that, I conclude this session.
And thank you, Shubhadeep, for organizing such a organized program. Thanks, Shubhadeep. Thank you, sir.
Very beautifully
KL
conducting
Sahu,
the
sir,
session.
for presenting such a nice webinar. Thank you, sir. Thanks a lot.
Thank you. I'll leave.
Thank you, sir. Thank you, sir. This is Shubhadeep Paul signing off.